Alright. So we are building AST today. Right? So on previous streams the problem was I was thinking about how to parse this one, right? And what I came up with, there is like an algorithm invented by Dexter. I forgot, like I've googled it before. Something yard. Shutting yard, yeah. Shunting yard. And as far as I understood, that's like pretty much basically the same thing I was planned to do, right? And I also read that it's like probably not the best way to do it because it's like complex. It's a state machine and like yeah. So there should be another way. So I guess I'll just like research it, right? I just look for what are the ways to do it and just learn about them. How do I ask it? Boolean AST. Parsing. Expressions. Methods. Ways. Parsing arithmetic expressions. Example. Actually, you know. I'm building a programming language in C. I wonder what are the ways to parse tokens of arithmetic expression to an AST. So there is like, I guess the most obvious approach, right, is to go through everything and do the higher priority work first, right? But it's like, I'm not sure how it's gonna work, right? Because like parentheses are always higher than some multiplication. So here I have to go one more time, seek for multiplication first. I have to go here like 3 to search for another parenthesis inside, and like I'm not sure. Let's break down the most common and practical ways to do this in C. The prerequisites. No matter which parsing method you choose, you need two things first. A Lexer tokenizer. This component reads your source code string and turns out it's string tokens here. Yeah, I had this one. An AST node structure. This is the data structure you will be building for arithmetic expressions. A node can be a number, a leaf, or an operator, an internal node with the children. Type def num node, number, binary operation. AST node. Node type. Union. Node number, double number value, okay. And now binary op. Token type OP. We don't have OP here, right? AST node left, AST node right. It's actually much better than what I'm doing here. Helper function to create nodes, color command. Yeah. We'll also need a function to freeze the tree. Okay. Let's explore the main parsing methods. Recursive descent is descent, right? Parsing. Pred parsing is a variation. This one I read about. Think about powerful pred parsing. Yeah. This is the most common and intuitive method for hand writing a parser. The structure of your code directly mirrors the grammar of your language. Okay, the key idea is to use a set of mutually recursive functions to parse the language hierarchy, to handle other precedents. We define our grammar in levels. Yeah, so like with an expression, term plus minus, term, multiplication. Term is like number, right? Term, factor, multiplication, division, factor, factor, number, parenthesis, expression. Also, it's the other way around. So factor is a number, term is multiplication, and expression is like plus and minus. This grammar encodes the precedence plus the precedence, multiplication, and division are in the term rule, which is lower in the hierarchy. So they're evaluated before plus and minus from the expression rule. I still do not like quite understand how does it parse it, right? Like, I understand this segmentation on levels, but how do you build a tree? Very intuitive, easy to debug, good error reporting, is easy to add. Cons can be tricky with certain grammars, like left recursion, which we handled here by using while loop. What is left recursion? In formal language theory, left recursion is a special case of recursion where a string is recognized as part of a language by the fact that it decomposes into a string from the same language on the left and the suffix on the right. For instance, 1 plus 2 plus 3 can be recognized as sum because it can be broken into 1 plus 2, also a sum, and plus 3 as suitable suffix. Yeah. I don't get it. I don't get it. Actually, let's create new chat. Actually, it's important in context, so like, I'll just delete the last message later. What is left recursion? The Shantin-Yard algorithm, yeah. The algorithm is specifically designed for parsing mathematical expressions. It doesn't use recursion, instead it uses two stacks, one for operators and one for values, or in our case AST nodes. The algorithm produces a reverse Polish notation stream, which can then be trivially converted to an AST. A more direct approach is to build the AST on the fly, yeah. The algorithm AST Boolean variant. By the way, like, I don't understand this algorithm too. Like, I fed my code, I gave my code to Gemini, right? And it says it's like, it's, actually I didn't give it because it's like, it's not complete, right? I explained what my idea was, and it said it was a Shantin-Yard algorithm. But I still don't see, like, how are they the same, right? Maybe I'm just like, the point is that, like, I was doing that on the fly, but I don't know. Methods you're using, a parser generator. This is probably not my method, right? Based on Yak. For language projects, you might not want to write the parser by hand. Tools like GNU Bison, the modern version of Yak, generate the C parser code for you from a high-level grammar specification. You would write a .y file. No, I want to write it myself. You would compile this file with, yeah, okay. Manual mirrors grammar. Actually, like, this point that mirrors grammar, it sounds pretty cool. I feel like it should be cool to use. Manual use text, okay. Easy learning, easiest, very intuitive, medium. Parser hires to require learning the tools and syntax, okay. Flexibility, high. Easy to add custom logic, low, specialized for infix expressions. Okay, so like, this one looks like the best for everything. Error reporting, excellent, you control exactly. Fair, good, okay. Best for learning simple to medium language to control. Formatting a calculator or just expression parsing part of language. Let recursion is fundamental concept in parsing theory, and understanding it is crucial, especially when you're handwriting a parser. In the context of formal grammar, a rule is left recursive if the first symbol on the right hand side of the production can derive the non-terminal on the left hand side. The fuck it means? There are too many types. Like, I feel the fact that I've been learning like math not in English, it makes me so much dumber in math in English. Like, I just so hard to read it. Direct left and recursion. This is the most obvious form. A rule is directly left recursive if looks like this. A arrow A alpha. Huh? Where A is a non-terminal, like expression, and alpha is some sequence of terminals and non-terminals, like plus term. Why are they called terminals? What are terminals? And why are they called that way? I feel like I'm missing on a lot of fundamentals. Think, please. I understand that, like, Gemini, like, a studio is free, right? So, like, they have to save costs, but please think. Let's go. Prompt engineering. It's the absolute bedrock of parsing language theory. Okay, let's break it down. The analogy, English grammar. I'm not sure if it's a good analogy for me. Okay, let's try. Think about how you learn grammar in school. You were taught rules like a sentence can be a subject followed by a verb, yep. A subject can be a noun, yep. A verb can be, well, a verb. Wow, a noun can be, well, a noun, okay. In this system, the concepts in backticks, sentence, subject, verb, noun, as abstract grammatical categories, yeah. They describe parts of the structure, yeah. The actual words you use, like cat, runs, dog, barks, are the concrete words that make up a real sentence, yeah. Now let's map these to programming languages, terminal and non-terminals. Terminals. A formal grammar for a language, whether it's English or C, is a set of rules for how to build valid sentences or programs. These rules use two kind of symbols. Terminals, the words. A terminal is a fundamental, indivisible symbol of the language. It's an atom. It's pronounced atom, right? Or atom. Can I... Atom. Okay, atom. It's an atom that cannot be broken down into smaller parts by the rules of the grammar. Terminal, right? In UC code, terminals are your tokens. Yeah. So why is it terminals and not tokens? Like, why do I need two words to name one thing? Like, I mean, I understand that terminal is like more abstract, right? Examples. Keywords like if, while, return. Yeah, so they're basically tokens. Token type representing literals like token number or token identifier, yeah. Associated with the token, but the parser just sees the category token number, yeah. The lecture is the part of your compiler that reads the raw text and produces a stream of these terminals tokens. Non-terminals, the concepts. Non-terminal is an abstract high-level grammatical concept. It represents a set of possible sequences of terminals. Yeah, like if statement, right? Like multiplication. A non-terminal's purpose is to be replaced by its definition. A non-terminal's purpose is to be replaced by its definition, which is made up of other terminals and non-terminals. Okay, In your recursive decent parser, non-terminals are your parsing functions. Examples: expression, term, terminal, factor, statement, declaration. You never see an expression in your source code, you see 3 plus 4, and your parser recognizes that sequence of terminals, token number, token plus, token number, as mentioned the rule for an expression. Yeah. Parse called terminals. This is the most insightful part of the equation, and the name is beautiful descriptive once you understand the process of derivation. Wow, okay. How can we get to derivations? Derivation is a process of starting with a single high-level non-terminal like program and repeatedly applying the grammar rules to expand it until you are left with only a sequence of terminals. Is it derivation? Wait, I have such a skewed representation of derivation. Like, parse tree. Okay, so there are like several definitions, right? Math. Where's math? Am I confusing it with another word? Derivative, yeah. My bad. Fuck, why is it so difficult? Derivative definition. And derivation is like another branch, right? Imitative of the work of another artist. Yeah, so it's like the speed of changing, right? Of a product having a value deriving from an underlying variable asset. Okay, let's go back. Derivation. Meaning the action of obtaining something from a source or origin. Okay. So it's like branching, right? I mean, in some sense. The set of stages that link a sentence in a natural language to its underlying logical form. Okay. Derivation is the process of starting with a single high-level non-terminal. Yeah. Let's trace the derivation for 3 multiplied by, in parentheses, 4 plus 5. We start with the highest level concept expression. Expression is a non-terminal, we must expand it. We apply the rule expression to term. Wow, how do I even read it? Term is a non-terminal, we must expand it. Term is so it's like 3, right, and 4 plus 5. We apply the rule. Term multiplied factor. Fuck, what the? Wow. I want to use this one actually. I feel like this one might be better. What language is this? FN. Wait, it's Rust? Okay. Okay. Wasn't ready for that. I guess Rust actually should be really sweet language to write and other languages in it, right? Because of its like types flexibility. Okay, so let's go back. The problem infinite loops in top-down parses. Do not do this. This will cause an infinite loop. To parse an expression, the first rule says we must parse an expression. We will never reach this code. Yeah. I mean, it's like quite kind of obvious, isn't it? Like, do we need specific term for that? Okay, let's just omit it for now, right? Just keep it. Thread parser. Okay, let's read this one, right? Simple but powerful thread parser. Okay, previous one felt better. There were more examples. Welcome to my article about thread parsing, the Mona tutorial of syntactic analysis. I don't like this combination of words. Like I have some like immediate stress feeling. The number of part-parsing articles is so large that they exist as server posts. Wait. Part-parsing index and updates. Oh, okay. Wait. That's where am I, right? That's where I am. Rust. Elm. I know Elm. But Elm is functional. TypeScript updates. Pet parsing and precedence clubbing are the same algorithm. What? I want picture, please. Okay, it didn't help. Okay, let's go slowly. In this article, I will clarify some confusing terminology in the world of parsing, which spans online resources and computer science publications from 70s and 80s. This is based on my experience writing parsing, shell, arithmetic, e.g. Yeah, ground. Wikipedia has separate pages for, and the later mentions prestigious climbing as an alternative to pred parsing. What is operator precedence parser? Okay. Example execution of the algorithm. An example execution on the expression 2 plus 3 multiplied by 4 plus 5 equals if is equal 19 is as follows. We give precedence 0 to equality expressions and 1 to additive expression, 2 to multiplicative expression. Precedence is like the level of importance, right? Parse expression 1. LHS equals 2. In precedence equals 0. Is it like... OP is plus. Wait, the look ahead token is plus. With precedence 1. The outer while loop is entered. Operation is plus, precedence 1. And the input is advanced. RHS is 3. Like, I'm just so confused about naming. Like, I don't know what precedence means. I don't know, like... Okay, I guess it's pretty much... I know, it's just... My brain just refuses to parse it. Meaning, precedence. The condition of being considered more important than someone or something else. Priority in importance, order, rank. Okay. So it's like a priority. Precedence 1. And the input is advanced. RHS is 3. What is RHS? Computer science and operator precedence parser is a bottom-up parser that interprets an operator precedence grammar. For example, most calculators use operator precedence parser to convert from the human-readable infix notation relying on order of operation to a format that is optimized for evaluation, such as reverse Polish notation. Wait, wasn't it? Okay. Okay, I guess they like doing the same thing. Like this Shantin-Yard algorithm. Dijkstra's Shantin-Yard algorithm is commonly used to implement operator precedence parsers. So like they're the same, or aren't they like what? Okay, the goal of this particular article are raising any issues that the so-called left recursion problem is overstated. What does overstated mean? Is it like stated too strongly? Okay, so it's like not a problem, right? That's like it's not as a big of a problem as everyone says it is. Complaining about inadequacy. Complaining about inadequate. Fuck, how do I even read it? Inadequacy. Inadequacy. Wait. Wait, how do it's isn't it? Why she reads it like in? Oh, she reads it like SN. Inadequacy, okay. Inadequacy of BNF for representing infix expressions. What is BNF? Providing a description and implementation of prot parsing. Algorithm which sticks to the core and doesn't introduce a DSLE abstraction. Understanding the algorithm myself for hopefully the last time. I've implemented a production grade pret parser once, but I no longer immediately understand that code. Okay, like this sentence makes me feel better. Like it seems like I'm not the only one who struggles. This emoji is insane. The fuck? What is that? Why it wow, it's so bad. This minus is just so understanding the yeah. This also seems a fair bit of familiarity with parsing techniques, and for example, doesn't explain what a context-free grammar is. That's bad. I don't know what context-free grammar is. For newbie, is there like such thing? Do I have to watch video? 30 minutes? Wow, that's insane. 22 minutes. Reddit. This seemed to be a pretty good explanation. Fuck. If you want good video, this stuff. Do I have to use like I feel like LLM might be the best one or one of the. I just like this one scares me away. I don't know what context-free grammar is. Context-free grammar. Informal language theory. In logic, mathematics, computer science, and linguistics, formal language is a set of strings whose symbols are taken from a set called alphabet. Wow. Wow. Okay. Context-free grammar. Context-free grammar is a formal grammar whose production rules can be applied. Production rules? Formal grammar is a set of symbols and production rules for rewriting some of them into every possible string of a formal language over an alphabet. Whose production rules? Computer science production of production rule is a rewrite rule that replaces some symbols with other symbols. A finite set of production P is the main component. Wow, can be applied to non-terminal symbol, regardless of its context. Oh, I see. I don't. In particular, in the context-free grammar, each production rule is of the form A to alpha? Simplified excerpt of the formal grammar. Oh yeah, it's like, it looks relatively simplified, yeah. Okay, actually I might understand what's happening. So like, we got this expression, right? If x is more than 9, damn, it's so bright. Why is it like, why does it have light dim? X equals 0, y equals else, right? It's else. If this, oh no, it's like, it's just two statements. If x more than 9, then x equals 0 and y equals y plus 1. ID, number. P expression, P expression. A expression, P expression. Y equals A expression. AD equals R expression. So it's like, it represents how it parses it, right? Like, STMT. Okay, let's keep context-free grammar for now. Parsing is a process by which a compiler turns a sequence of tokens into a tree representation. Yep, There are many approaches to this task, which roughly fall into one of the broad two categories: using a DSL to specify an abstract grammar for the language, handwriting the parser. Yeah, we are choosing the second one. Pre-parsing is one of the most frequently used techniques for handwriting parsing. BNF. The pinnacle of syntactic analysis of or according to syntax. Okay, I mean, makes sense. Yeah, it's like an adjective. The principle of syntactic analysis theory is discovering the context-free grammar notation, often using BNF, concrete syntax, for decoding linear structure into trees. I do not understand it. I remember being fascinated by this idea. Oh yeah, sure thing. Okay, I guess we should go like level lower, right? Or higher, how depends like how you see it. How to write a compiler. Actually, a lot of compilers don't compile all the way to binary, not on their own way. But like, I don't care what a lot of that. I want to like write and see compiler. Part 1. Update. Integers. Turn 2. Lexing. The lexer, also called the scanner or tokenizer, is a phase of compiler that breaks up a string, the source code, into a list of tokens. A token is the smallest unit the parser can understand. If program is like a paragraph, tokens are yeah. Now that some tokens have. Okay, what tokens do we have here? Int, main identifier, open parenthesis, close parenthesis, open brace, return keyword, constant 2, semicolon, close. Yeah. Now that some tokens have a value. Yep. Here's the tokens your lexer needs to recognize and the regular expression defining each of them. Do you recognize tokens by regular expressions? That sounds terrible. If you want, you could just have a keyword token type instead of different token type for each keyword. And have like value for it? I don't know. Doesn't sound good. Parsing. Here's see the code for constructing this AST. Wait. Should we watch a video? Let's try to watch video actually. Let's just try. Unlike
this video was sponsored by Codecrafters.
1.5x.
Parsing is simply the process by which a program receives a sequence of tokens and turns that sequence into a tree representation.
Yep.
In Python, for example, when we input something like 1 + 2 × 3, the interpreter should perform the multiplication before the addition. Here, the parsing process must result in a data structure that tells the interpreter that the expected result is the addition between 1 and the product of 2 and 3. This tree representation is vital in the domain of implementing programming languages, because it organizes and represents the structure of programs in a way that mirrors the rules of the language we want to create. For example, if for some strange reason we wanted to create a language where addition has higher precedence than multiplication, the resulting tree would look like this. And this is what this video is about: manually processing the input code to produce a tree that follows our rules. Today, we're going to learn about an algorithm called Pratt parsing, one of the simplest yet most powerful techniques for manually parsing expressions. And by the end of this video,
it sounds so offensive when he says one of the most simplest, and I just like spent half an hour already just don't understand anything.
Capable of evaluating complex expressions. Hi friends, my name is George, and this is Core Dumped. There are roughly 2 ways to parse text input. We can do it all by ourselves, but another common approach is using a domain-specific language to specify and abstract the grammar of the language we are creating.
Yep.
A good and common example of this that I recommend reading about is BNF. The approach we're covering in this video, Pratt parsing, is one of the most frequently used techniques for handwritten parsing. The first thing we are going to do is define some rules. First, we are going to start working only with infix expressions. Depending on the reception of this video, we might cover prefix and suffix operations on another video. Only with infix expressions. Depending on the reception of this video, we might cover prefix and suffix operations on another video. And second, we are going to work exclusively with single character numbers and variables. Numeric values can range from 0 to 9, and variable identifiers are 1 character long. This is to keep things simple, since we need to create a component called a lexer, which takes the string and generates a list of structures that we are going to call tokens.
Okay.
So let's define tokens. For convenience, I'm using Rust here, so I can define a token as an enum, which can be either an atom or an operator. It
Convenient.
might be more intuitive to refer to atoms as operands. We are also going to define a special token to represent the end of file. Our lexer will simply be a structure that contains a list of tokens. Since we are working with single characters, the process of generating tokens is actually pretty simple. We receive the source code as text, split it into characters, then yield everything that is not white space, and map each element into a token. If it is a digit or a letter, it becomes an atom. Otherwise, we treat it as an operator.
Makes sense.
All tokens are collected into a list, which we use to create and return the lexer. Next, we need to define how the
like
a digit or a letter, it becomes an atom. Otherwise, we treat it as an operator.
becomes an atom?
All tokens
Why
are
he
collected
have
into a list.
both identifiers and values as atoms? It's kind of confusing. Won't it be like? I got a huge bug here. Wait a minute. Okay, one problem solved. Let's proceed. Was it that way? It was a little bit... Wait. Or was it lower? I don't remember actually. It doesn't matter.
Which we use to create and return the lexer. Next, we need to define how the tree will represent the parsed expression. Notice that an expression can be either a single atom, like a number or a variable, but it can be also an operation between other expressions. Once again, we can take advantage of Rust's type system. Instead of using a generic tree data structure, we define an expression enum that can be either an atom or an operation. In the case of an operation, we also need to store the operands, here as a vector of other expressions. For example, the variables in the expression can be parsed as atomic expressions, while the product of those two variables can be parsed as an operation, whose operands are the two atomic expressions we just parsed.
Wait a minute, like I have to like think through it. So you got an enum, right?
For example, the variables in
Expression is either atom with character, operation with character, and other
the
expressions.
expression can be parsed
Okay.
as atomic expressions, while the product of those two variables can be parsed as an operation, whose operands are the two atomic expressions we just parsed.
Yeah, makes sense.
We can do the same with the division, and then the same for the entire expression. And that would be the result of parsing the expression. Our job now is to write an algorithm that takes the list of tokens produced by the lexer and outputs this tree. Testing trees can be tedious, but since we are exclusively parsing expressions, we can format the tree as a string, where each operation is written inside parentheses with the operator first, followed by the operands. Here are some examples.
Wait,
This
let's keep that.
can be tedious, but since we are exclusively parsing expressions, we can format the tree as a string, where each operation is written inside parentheses with the operator
Oh, is it a Lisp? Is it Lisp mentioned?
followed by the operands. Here are some examples. This is commonly known as prefix notation, but more specifically, in the context of programming languages and compilers, this style of fully parenthesized prefix notation is typical of symbolic expressions, which come from the Lisp family of languages.
Yep.
This way, we can test our algorithm by comparing strings, as I'll show in a bit. This is where Pratt parsing begins. Here's one trick to help understand the algorithm, which I learned from an article. Instead of thinking in terms of whether one operator has higher or lower precedence than another, we talk about binding power. Every operator has a binding power. For example, addition and subtraction might have a binding power of 1, while multiplication and division might have a binding power of 2. And what our algorithm does is simply bind atoms to the operator with the stronger binding power.
What it does?
And what our algorithm does is simply bind atoms to the operator with the
Bind atoms to the
stronger
operators.
binding power.
I don't
Consider
quite
this
see it.
expression.
Okay.
All atoms in the expression have to move either to the right or the left. The binding power of the surrounding operators determines the direction. For example, the first atom, A, moves to the right toward the plus sign, since there's no operator to its left and hence no competing binding power. The next atom, B, does have an operator to its left,
I see.
but it moves to the right because the star operator has higher binding power than the plus. The atom C moves to the left, since the star operator to its left has more binding power than the plus to its right. Next, the atom 2 moves to the right, since the division operator has more binding power than the plus sign. And finally, the atom 4 has no operator to its right, so it moves to the left. That's the core principle our algorithm uses to handle precedence.
Mm-hmm.
Atoms move toward the operator with higher binding power. Whenever we find an operation that should be performed before another, a tree is created. And since parsing isn't finished yet, the process continues.
Yeah, like,
Find an
at this,
operation that should
at
be
this moment, right?
performed before another, a tree is created.
So at this moment, we have several trees, unconnected, right? And we have, like, stored them in some way. And then we have, like, connect them into a single big tree.
And since parsing isn't finished yet, the process continues. These trees now become operands and must themselves take a side. But sometimes, an operand might have the same operator on both sides. So, which side should it move toward?
The first
Since
one,
addition
left.
is associative, it wouldn't technically matter.
Yeah.
We could allow the algorithm to choose randomly, but for testing and consistency, we want it to behave deterministically. To avoid this dilemma, we'll introduce a subtle solution. We assign each operator slightly more binding power on one side than on the other. That way, the algorithm still behaves as described before, but when encountering identical operators on both sides of an operand, that tiny difference in binding power ensures it moves toward one side in a predictable and testable way.
Okay.
That being said, let's write some code. But before that, a quick message from today's sponsor. Once the source code has been tokenized by the lexer, we need to iterate over the sequence of tokens. We'll need two methods. The next function, which simply returns the next token in the list while consuming it, meaning that each time we call it, we mutate the list. And the peek function, which allows us to look ahead at the next token without consuming it. Since I'm using a vector, I'll reverse the list when it's created. This makes it more efficient because we can use pop to retrieve tokens from the end of the list, which is faster than shifting from the front.
Huh?
And there's nothing left more efficient ahead at the next token without meaning that each time we call it, we mutate the list. And the peek function, which allows us to look ahead at the next token without consuming it. Since I'm using a vector, I'll reverse the list when it's
Reverse a list? Why would you?
created. This makes it more efficient because we can use pop to retrieve tokens from the end of the list,
Oh, okay, okay. I mean, it's like, okay.
which is faster than shifting from the front.
Mm-hmm,
When
okay.
there's nothing left to pop, it means we've reached the end of the file, so we return the special EOF token.
Yeah, so he, like, still goes from the beginning, right? He just, like... Oh, my bad. He just turns it other way around, it goes from the back, which is, like, yeah.
We'll also need a function that receives an operator as a character and returns its binding power as a tuple, giving us the left and right binding powers.
Mm-hmm.
If the operator is unknown, the function should panic. Next, we'll define a function called parse expression that receives a sequence of tokens and returns an expression, which is our tree. And
Yeah, a sequence of tokens. Okay.
since we need to test this, I'll create a method for our expression data type called fromString that simply tree. And since we need to test this, I'll create a method for our expression data type called fromString that simply creates the lexer and then calls parse expression.
Mm-hmm.
This allows me to easily create an expression tree from a string in our tests, and then assert that the resulting tree, when formatted as a string, matches what we expect. Now, something I want you to notice is that our algorithm can't exactly do what's shown in this animation, at least not all at once. Computers work sequentially, so we need to parse the string from left to right. We'll start with simple expressions, like these. Any valid infix expression should have at least one token. So, we call lexer next to consume the first token, which must be an atom. If we find an atom, we create an atomic expression from it. If the token is not an atom, we panic and output an error message, simply saying, bad token.
Okay.
But if the token is an atom, we'll store the atomic expression created from it in a variable called left-hand side, since we're parsing from left to right.
Left-hand side,
After
okay.
that, we don't know whether
That's what
tokens
LHS
in a
is,
variable
right?
called left-hand side, since we're parsing
Makes
from left
sense.
to right. After that, we don't know whether there are more tokens to parse, so we call peek to check. If there are no more tokens, it means we're done, and we can return the atomic expression we just created. But if we do find another token, we expect it to be an operator, since we're working with infix expressions. In that case, we store the symbol. If instead we find another atom, we panic, because we don't expect two atoms directly next to each. In that case, we store the symbol. If instead we find another atom, we panic, because we don't expect two atoms directly next to each other in an infix expression.
Okay.
Once we've confirmed it's an operator, we consume it by calling next. And now, since we've just read an operator, we know the next token must be an atom. So, we call next, again, and match the result. If it's an atom, we create another atomic expression to represent the right-hand side. If it's not, we panic again. Now that we have both atomic expressions, we can assemble the more complex expression by creating an operation expression with the stored operator and the two operands on each side.
Huh? Wait, what?
Expression by creating an operation
Also, it's like, wait, no.
expression with the stored operator and the two operands on each side.
Okay.
Pretty simple, right? Well, things get more interesting when we consider larger expressions.
Okay.
In these cases, we can't just assume that the third token is the right-hand side of the first operator, because the second operator in the sequence might have more binding power.
Yeah.
In fact, since all of this has to be done sequentially, there's no way to know from the start whether the
We're
expression
actually doing something really similar to
in
this
fact is the
right now.
right-hand side of the first operator, because the second operator in the sequence might have more binding power. In fact, since all of this has to be done sequentially, there's no way to know from the start whether the expression contains more than one operation. So, the function we just wrote isn't actually very useful.
Yeah.
So while iterating, before parsing the current part of the expression, we should first fold the operation with higher precedence. This is where we rely on recursion, allowing the function to call itself to handle inner expressions. But that alone isn't enough. Notice that result of the recursive call might not actually be the right-hand side of the current operation, because the next operator could still have higher binding power than the current one. The solution is to use a loop after parsing the left-hand side, so the function can continue calling itself recursively to fold deeper expressions until it finds an operator with lower binding power than the current one. To do this, our function needs to receive the right side binding power of the caller's current operator, so it can compare it with the left side binding power of its own operator and determine when to break the loop. The binding powers, of course, come from the function we defined earlier. And believe it or not, that's it. I know some of you prefer visual explanations of what the code is doing, so here's an animation that follows the algorithm through each iteration and recursive step. I recommend slowing down the video if you need a moment to catch up with what's happening.
Oh, I really need a moment to catch up, honestly, because, like, the hell is happening?
And determine when to express the left one. Current op. Notice. But that alone isn't enough. Notice that that result of the recursive call might not actually be the right-hand side of the current operation, because the next operator could still have higher binding power than the current one. The solution is to use a loop after parsing the left-hand side, so the function can continue.
Use a loop after parsing the left-hand side. Okay.
Calling itself recursively to.
So what is he doing here? He checks the first tokens and he starts a loop. He checks next token, right? Pick. And the file break. Operation return OP. Okay. We get the operation. Going next. Right hand side. Parse expression. Lexer. Okay, so it starts a recursion, it goes here. If it's... So we already have operation, it's only atom is allowed. Yeah, that makes sense. That makes sense. Then go in here. But it's like, it's always gonna be called, right? When it will stop? When it's gonna be like end of file, right? That's the moment it's gonna stop here, yeah. So it goes like until the very end. Expression, operation, OP. Okay, yeah, I kinda see it. I kinda see it.
Expressions until it finds an operator with lower binding power.
And this one just returns, right? Return. Wait, why do we return left hand side? Oh, because we assign it. Yeah, we assign the new expression to left hand side. Yeah.
The current one. To do this, our function needs to receive the right side binding power of the caller's current To do this, our function needs to receive the right side binding power of the caller's current operator.
Right side binding power? Why is it right side?
Our function needs to receive the right side binding power of the caller's current operator, so it can compare it with the left side binding power of its own operator.
Huh? Wait.
Caller's current operator, so it can compare it with the left side binding power of its own operator.
Left binding power, right binding power, infix binding power operation. If left BP is less than minimal BP break.
And determine when to break the loop. The binding powers, of course, come from the function we defined earlier. And believe it or not, that's it. Okay,
so we get the binding power of operation in a tuple. Why do we need... Oh, we need... Wait. Right binding power, so we like check the end, right? Because we're going like only forward, we need only the end binding power, right? That's because we're using right binding power. It kind of makes sense, I guess. Like I don't quite... I don't fully see it, but I guess it makes sense.
That's it. I know some of you prefer visual explanations.
So it takes A.
Of what the code is. That's it. I know some of you prefer visual explanations of
0 less than 1. What do you mean? No operator.
What the code is doing. So.
Huh? Wait. What the hell just happened? Oh, this one, right?
Come from we defined earlier.
I'm confused.
Believe it or not, that's it. I know some of you prefer visual explanations of what the code is doing.
Parse expression.
So here's an animation that follows. I know some of you prefer visual explanations.
Okay, so we got 0 by default, right?
The code is
yeah.
doing.
Makes sense, makes sense.
Animation that
So now 2 is more than 1.1, yeah. So we create another parse expression inside,
through each iteration,
right? 2.1 is more than 2.
And recursive step.
Okay.
I recommend that follows the algorithm through each iteration and recursive step.
Yeah, it's pretty
I
good.
recommend slowing down the video if you need a moment to catch up with what's happening. I recommend slowing down the video if you need a moment to catch up with what's happening.
That was pretty good.
I've written some tests here, and now they all pass. But we're forgetting something important. Parentheses.
Good point.
Sometimes we need an operation with lower precedence to be evaluated before one with higher precedence. To do that, we use parentheses to explicitly specify the order of operations. However, our current code doesn't handle that yet. So if we try writing some tests with parentheses, they will fail. Fortunately, this is easy to fix. Notice that since the parentheses characters are neither digits nor letters, the lexer will classify them as operator tokens. The reason our test fails is that every time we call our parse expression function, it expects the next token to be an atom. If it's not, it panics. But now that we know expressions can also start with an opening parenthesis, we can handle that specific case. Since we expect any kind of expression inside parentheses, the function can simply call itself recursively here. However,
Wait.
we
Seriously?
explicitly pass 0 as the minimum binding power in that recursive call. That tells the parser to fully fold the expression inside the parentheses, regardless of any operator that may exist outside them. Next, we need to handle the closing parenthesis, which we know can never appear at the start of an expression. It must appear inside the loop, marking the end of the parenthesized expression. So, whenever we find a closing, it must appear inside the loop, marking the end of the parenthesized expression. So, whenever we find a closing parenthesis, the loop should break. That means the algorithm has finished parsing the inner expression.
Okay, that's pretty good,
There are
yeah.
two ways the loop can exit. When we use a recursive call because we found an opening parenthesis, we must ensure that the recursive call returned because it found a closing parenthesis. Otherwise, malformed expressions, like an opening parenthesis with no recursive call return, two ways the loop can exit. When we use a recursive call because we found an opening parenthesis, we must ensure that the recursive call returned because it...
Let's run next. Oh, shit. Wait, what? Oh, so we check if next token is close parenthesis,
found a closing parenthesis. Otherwise, malformed expressions, like an opening parenthesis with no matching closing one, could be incorrectly treated as valid. And that's pretty much it. If we run our tests again, they'll now pass. And that's how Pratt parsing can be used to parse infix expressions. What I really like about this algorithm is that if we want to support new types of infix operations, we don't need to touch the core logic at all. For example, if we wanted to support exponents and roots, all we have to do is assign symbols and specify their binding powers in the appropriate function. No changes to the parser logic itself.
Sweet.
Just keep in mind that associativity matters. Unlike addition, where the order didn't really matter, exponents are usually right associative. So the expression a to the power of b to the power of 2 typically means this. Exponents are usually right associative. So the expression a to the power of b to the power of 2 typically means this.
Why?
To reflect that in our parser, we assign a higher left binding power than right binding power for the exponentiation operator.
Yeah,
Again, this is
smart.
entirely up to us and the rules we define for the language we're implementing.
Smart.
Not too hard, right? In fact, this same approach is also commonly used to parse function chaining with the dot operator. A line of code like this is also an expression. If we assign a binding power to the dot operator, Pratt parsing can build a tree from it just like any other expression. Unfortunately, I can't show you this in our example since our lexer can't tokenize identifiers, but it's important that you know this, especially if you're planning to build a compiler. Arrays, prefix and suffix operators, and even fancy cases like the ternary operator.
Oh, so you mean like I'm building this...
Arrays, prefix...
What's it called? I already forget the name of the algorithm. Pratt parsing, right? Is it Pratt? Pratt parser, yeah. It's like I can use it for everything, pretty much.
And even fancy cases like the ternary operator. All of them can be parsed using Pratt parsing.
I don't want ternary operators, honestly.
The article that inspired this video explains it really well. I'll leave a link in the description in case you want to learn more. And now, we're going to use this algorithm to build a tiny interpreter capable of evaluating expressions. To keep things simple, we're only going to support a handful of operators. It might not seem like much.
I guess it doesn't matter, like this one I probably will be able to manage. So let's turn on some music. Too loud, way too loud. Okay. Actually, let's start with rewriting an expression, right? So we got op and atoms, right? Operations and atoms. union expression is either operation, right? How do I do that? I create another union. Operation. Actually, it's atom. So it's like type. Actually, let's create another type to this because it looks really bad. Type def. Atom. Oh, it's like union, right? Here we write atom. So it's either an operation or an atom. No, I'm writing that. What am I doing? Wait, I'm writing atom. What atom can be? It's not a union, it's a struct. And that, struct. Type. Let's create another enum here. Atom type. Looks like can be addition. Wait, what is? I'm still kind of confused. Wait, I try to replicate the way he does it, but like I try to reason like why, how does it make sense, not like how he does it. So atoms are pretty much like. So he builds. It's like a part of tokens, right? Yeah, I'm just calling them tokens, isn't it? It should make sense. Atom maybe. I guess not really. Yeah, so like he has a num token. A token can either be atom or operation. And atom is stacked union as well as operation, and so that's something I can do in. Can I? I can't. Can I? So here I got token type, which can be atom, operation. But what's the problem of having like operation not being like text with value, right? Too many errors emitted, stopping now? Okay, that's funny. Token type null, number, plus, minus, asterisk, slash. But how it will work like with keywords? Yeah, I guess like I like my approach more. Like I like when it's like, yeah, split it in different token types. Let's release this for now. So got expression type. Wait. Oh, wait. Why do I have... Token is token type and value. Yeah, and value should probably be like string, not an integer. But I guess that's okay for now. Okay. This one looks pretty good, right? Tokens are good. I got types, I got value. I can make it, you know how I can make it? I can make union. A union. Where it's either how do I do it? Like token with value, you know? Like this one, and just token. Do I need this? It will still take the space of the largest one, right? So it's like, doesn't matter. And I don't feel like it's gonna simplify code. So expression. Has he shot like... How he does expressions? Tokens. Lexer. Yeah, just tokens. Enum with atom or operation. Okay, I see. That's why he names them. That's why he names them atoms and not tokens, right? Atoms and operations, because it allows him to reuse in another context. The synonyms. Operation. No, it's different. They're different. Wait, no. It's Rust. What am I even thinking about? They're different. Yeah, he defines them right inside the enum. So it's like this, yeah. Yeah, it's different. Okay, so we got token type. Let's go to expression. Expression can be union, right? Wow, each expression has a vector. Each operation, yeah. Okay, yeah, expression can be either a token, right? It's just a token. Probably atom. Atom is... sounds better. Token type. An operation. Do I have to delete everything, actually? Why are there so many errors? I guess like it's gonna be full rewrite. Token type. Why is it token type? Will it work that way? Probably not. Or actually it might. No, it's not. It will work only for expression atom. Wait, how do I do it? Type def enum expression type expression atom type, I guess. So what can it be? Can be identifier. Wait, if it's an atom, it needs value. Expression atom is gonna be a struct, and it will hold let's copy this one. It's gonna be an enum expression atom type, right? So this here we're gonna use type. Damn, I feel like I'm repeating this logic, don't I? I do really repeat this logic. Expression atom type. Type. Here. What it can be? What it can be? Expression atom type number. Right? Can also be identifier. I guess it's it. Oh, it also can be parentheses. Mm-hmm. How do I break parentheses? Parentheses, yeah, I was close. We got type. And we need value. Yeah, actually, this is what it is. I feel like I went through a decent amount of information, right? I just have to like stabilize it.